Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. The topic was binary tree and the pattern is BST. So we'll see the very first question, which is convert a sorted array to binary search tree. Means we will be given the sorted array and we have to construct basically into a binary search tree. But before solving that problem, let's see what does binary search tree means. Binary search tree is a form of binary tree only, but the only condition is that every number towards its left subtree will be smaller than the root, and every node value or number towards its right side will be greater than the root value. Okay. Now the same rule follow for every node. For 2 also, everything which is smaller than 2 will fall under the left subtree and everything greater than 2 will fall under the right subtree. But remember that everything greater than 2, but it should be smaller than 5 also. Otherwise, that condition, every number which is smaller than 5 which should fall under the subtree would fail, right? Yes, so this is what binary search tree means. Now the question says that we will be given the nums sorted array and we have to make it a binary search tree. Okay, but before moving to the solution, let's see what does the constraint says. The constraint says the nums length can go from 1 till 10 power 4. It means the number of nodes can be from 1 to 10 power 4. Okay, and the values can also be from minus 10,000 to 10,000. Okay, it's safe. Why? Because integer can hold values up to 10 power 9. If it goes beyond this, then we will save this in a long format, and I hope you all know that, right? Okay, so basically we have to convert this nums array into a BST and the number of nodes are given O of n. So the optimized solution will be if we can do this in big O of n, right? Okay, so as the question already mentions that it's sorted array. So basically we can think about the binary search, right? Binary search means that obviously if the list numbers are given in sorted array, there will be some meaning, right? So the first condition is how to think what will be the root value. See, with this sorted array, there can be multiple subtrees possible, like multiple binary tree possible. How? Let's make minus 10 as root, correct? Then as minus 3 is greater, so go there. Now as 0 is greater, so go in the right side. Now 5 is greater, go in the right side. Now similarly, go in the right side. This is also acceptable. Okay. Now similarly, let's say minus 3 is a head. Then minus 10 is smaller, so it will come left side. 0 will go right side, 5 will go right side, 9 will go right side. Correct. Now similarly, if you make 0 as your node, then minus 3 will go here. Correct. Minus 10 will go here. Now 5 will come here and 9 will come here. This is also a binary search tree. So there are multiple possibilities and you have to return any one of that. But as the question says, convert it into a height balanced. And now what does height balanced mean? Height balanced, if you have saw that video where we have to check if the tree is balanced or not, I'll attach the link somewhere here. So balanced means if you start with minus 3, then minus 10 is a like left node, 0, 5, and 9 is the right side. So if you see the right depth means height, which is 1, 2, 3 and left height is only 1. So the difference between the left height and the right height, if it is greater than 1, which is here it is 3, right? So then it won't be a balanced binary tree. So as a question is saying make it balanced, height balanced, it means it's very much important because it is sorted. So let's pick the value which is at middle and consider it as a head node. So if we'll consider this 0 as a head node, then what will happen? Everything towards its left side will become the part of left subtree and everything towards its right side will become the nodes of right subtrees, right? So can we say, okay, this is a node, right? As we have made this as root, so definitely in the next function call, we have to send only this much nodes for the left side. As we have to make, send this as left, this for right in a function. So it is very important to close this or to send this in a recursive function, recursive call. Okay. So let's make a recursive call and let's say DFS where we'll get root. No, why not root? Because root we are creating, we'll be given this nums array, so we have to send this nums array, and as we have to pick this middle element with the help of index only, because we have nothing, like the tree has not been given, we have to create the tree. correct? So when we have to create the tree and the list has been given, so definitely we are going to select one node, one number to make root, correct? So hence in that case, that indexes will play the role. What role I'm talking about? The base case role. Why? Because as we are going to write the recursive function, so there should be some condition to stop it, right? So that condition will be, because we'll start left pointer and right pointer from here, and until our, like, if our left and right pointer pointing to same index, it means there is still one number pointing, correct? So there is still a chance to make a node at least. But when left crosses right, then we have to stop. So hence this will be the stopping condition for any recursive call, where root will not be given and where we have been given list or any like anything which has index. Okay, so with this we'll send a left index and with this we'll send a right index, correct? As said, the very first base case will be if my left has crossed right, then we have nothing to do, so we'll simply return. Now what will return? We'll see this very soon. Okay, so now as of now the left is here and right is here, correct? In the main function we'll send left 0 and right length of nums minus 1. But what will be the root? Now our task is to calculate the root. So root will be nothing but the middle index. So can we say ki let's calculate the mid index, which is nothing but left plus right minus left divided by 2. I hope you know how to calculate the mid index. This is the safest zone, right? Where we can have the left plus right, like where left plus right summation might go beyond 10 power 9. So there it will be integer overflow. So hence this is safer side where we are doing right minus left, okay? Right minus left, okay. So now we are done with the mid calculation. Now we have to make the root. So that will be of tree node type. Root is equal to new tree node and the value will be what? Can I say nums of mid? Yes. So nums of mid index will be my root. Yes. Now this is the root and our task is ki root is done. Now root has been created. Now our task is to make the left subtree and right subtree. So go towards left side and whatever this returns, connect this to root dot left. Similarly, whatever this right side will return, connect this to root dot right, correct? So can I say I'll call the two functions and I'll store it in root dot left and I'll store it in root dot right. But what function I'll call? I'll call for DFS where I'll send nums. Now, as we can see, nums remains same, but left and right is varying. So initially, we were allowed to take every element to make the bigger subtree. But now as 0 has been created and now we want to make the node towards the left side of the 0. So towards the left side of the 0 means we want every number which are smaller than 0. So if this is the middle index, can I say the index till where we will have smaller elements will be from left side till mid minus 1. Now similarly for right side, can I say mid plus 1 till right side? Yes. So here with nums, left will be as it is and right will be mid minus 1. Similarly for the next call, DFS nums, left will be mid plus 1 and right will be as it is right? Okay. Now what will happen? 0 has been created. We'll go towards left side. Now towards left side only this much is allowed. Again left will be this, right will be this. We'll calculate the mid index will be minus 10, correct? So we have to make this as root, okay? We have to make this as root. Now for this, again from left to mid minus 1, which is left only. Remember, left is 0, mid is what? 0. But if for minus 10 we'll send towards the left call, then the mid minus 1 will become minus 1. So right will become minus 1. And as they have crossed each other, so we have to return. Okay. So basically what we are saying, after minus 10, like in minus 10 left side, we don't have anything to put. So what to put? Return null, can I say? So hence when this cross, return null. Because in root dot left or right, we can only put tree node type. If it is not there, we can put null. So hence when the base case fails, we can say ki return null. Okay. So basically we have created one more node minus 10 and we went towards its left side and null. Remember, all these are not yet connected because it will get connected when we will return to this main root dot left. Then only we can say yes, it has been connected. Okay. I'm just showing you with the direction, but this has not been connected yet. Okay. Now, so tens towards left side we had nothing. Now for the right side what we'll say, this is mid index, right, which is 0. So we'll send mid plus 1, which is 1, and till right, which is 1 only. So we can say, okay, so towards the right side only -3 will get created. Now what do you think? What -3 should return so that -10 will get, like -3 will get connected to -10's right side? Can I say the -3 only, which is nothing but root only? Yes. So hence, after this, we have to return root. So what happened? We created -3, okay? -3 and left and right side has nothing. Why it has nothing? Because for -3, when you want to go there, you cannot move beyond this line, right? So in between we have nothing. Hence, in this case also, left has actually crossed right. Similarly, here also, this side also not allowed. So only -3 is there. So towards my left and right side of -3, we have nothing. So only null, null. Now once this has been created, once towards the left and right side of the -3, null has been added. Now our task is to return something towards their parent's right side, which was -. So for -10, like what -10 is waiting for? Any root value to get connected, and what is that root value? -3. So hence we have to return root, which is -3. So now we can say yes, -10 has been connected, okay, and this has been connected. Now what will happen? For 10 also, left was null, right was -3, sorry. Now what will get returned, which is root, -10. So -10 will get returned to where? 0's left side, and now this will get connected actually, okay. Now what will happen? We'll go towards right side, because this was only left call. Now we'll go towards right side, and for right side, left will be this, right will be this. Again, we'll calculate the mid index. Mid index will be 5. So 5 will become the root, and towards left it will have nothing, but towards right it will have 9. So we'll connect 5, we'll connect, create null here, connect this, we'll create 9 here, then we will connect this, okay. And now when we'll return 5 as a root, then 0 will get connected. So this is how our tree will look like: 0, 10, -3, 5 and 9, okay. And if you see the height of the left side, 1, 2, 3, and height of the right side, 1, 2, 3. Both are equal, their difference is not greater than 1. So hence it is a height balanced binary search tree. And that's what we are supposed to make, okay. Now if you are someone who gets confused, like when we are calling this function DFS calls, you would have seen ki somewhere to we are storing this, you know, in some variable, then somewhere we are just putting like this. Like when to make this, when to write root.left, and when to actually store in some trino type variable or integer variable. So basically, when you are constructing or playing with the data structure, which is tree here, we are creating tree here, right? So that is why whatever we are getting, we are not supposed to save it somewhere. No, we are supposed to attach in the root left or root right side. But when we are actually traversing in the root and we are not allowed to deconstruct the tree, we are only allowed to read the values or manipulate with summation. You can only allow to modify some values. Then whatever values we'll get from the subtree or root side, that we will store in the integer or node format, whatever is required and whatever we would have returned in the base case, okay. So always remember, when construction of tree is allowed, we, instead of storing, we change the and store it in root.left and right. Basically we are constructing the tree or deconstructing the tree if it has not been made. But in this case, so we are making it only, na. That's why. Now what is the time complexity? It seems it is sorted so of n, but wait. First 0 we have made, whatever nodes we have made, okay, even though it is sorted, but don't you think ki actually to create every node we would have went at that position to make and to install that node, right? So if n number of nodes are there, definitely the time taken will be O of n, right? Yes. And space complexity, as this is a recursive call, and you know in the recursive stack, once we only save one node from all the levels. Once we delete that, then only we go towards next side. So hence the number, like space complexity will be height, which is logarithmic of n. So this is the optimized code, okay. Now if you're thinking why can't we do with BFS, it is not possible with BFS. Why? Because in BFS we travel level wise, okay, but here with any single number of node, we have to decide whether to go or put towards left side or whether to go and put towards right side, right? This is what we are expecting to do. Like if we insert created this 0, then everything towards it we send towards the left side, which is not needed ki it will be in the same level, no. So hence DFS is the most suitable format to do this here, okay. So now let's write the code in the editor. So this is the editor we have. Now we have to make our build function. So whatever that build function will return, that will be root only, because our task is to create a tree and send root. Okay, so here we will send the nums, and here we'll send the index, which is 0, and last index, which is nums dot length -1. Correct. Now we have to make the build function, which is of type private. Return type will be tree node, because root we are going to return, and the function name build. Now integer array nums we will have. Now integer left we will have, and integer right we will have. The base case was ki if our left crosses right at any point of time, we will return what? Null. Why we will return null? Because we are trying to create the root, and if it is not there, return null. Now we have to create root, but first we have to find the middle index. So int mid will be left plus right minus left divide by 2. Okay, now once done, our task is to create the root first. Tree node type root is equal to new tree node, and the value will be nums of mid index. Okay, now we have to make root dot left side, and we have to make root dot right side. Okay, so we have to call the same function, which is build. Okay, we have to send nums. Now we have to send left. Left will be same, but right will be mid -1 for left subtree. Similarly, we have to send call the build function with nums. The left will be mid +1, and right will be right, because we are trying to go towards the right side. Okay, once done, we will return root to their parent for every node. That's it. Now let's run the code, and let's try to submit this. So this is the optimized code. Time complexity is linear, space complexity is logarithmic of n. I hope you understood. So this was the code in Java, and it was very simple. And here is the code in C++, and here is the code in Python if you're from Python background. So if you understood this, trust me, all the questions are going to be very easy from BST, at least construction and basic parts. And once we'll move towards the LCA and little more medium to hard level of problems, then it will become more interesting. So I hope you are doing this with basics. Basics means ki when we are returning this root, is it like this return statement is for the main function, or is it for every node? Okay, so how we have built here, we created the node first, and once it was not there, or when we are returning, then only we are getting, like, these nodes are getting connected. So if you are actually understanding with the basics level, trust me, the tree data structure, not only tree, graph will also become easy for you. So that's it. If you're done with this problem, go in the sheet and mark that question as done. Okay, I'll bring this question number at the first, because that should be in the first case. And now in the next video, we'll do the next question, which is again very easy problem, which is search in a BST. So that's it. Stay tuned, and let's meet in another video. I'll attach the sheet link and my social media links in the description. And if you're liking the way of teaching, please do hit the like button and subscribe the channel if not yet subscribed. Till then, keep learning, take care of yourself and your family.